So you might try statistics.
Nick, please go ahead.
Okay.
Third challenge, estimating risk bands using flood event data. Go ahead.
Okay, thank you very much. Can you hear me at the back, as they say? Yes, you can. Wonderful, thank you. Okay, well, I was privileged to be part of a team where basically I'm the only person who's not either a statistician or a hydrological expert, or possibly both. So, in some sense, my job is to be the front and interpreter for this team. And the challenge we took on is to basically, as it says here, the Environment Agency is looking for a simple tool where they can input a list of dates of flood events, by which I think we mean years, okay, and in return receive the confidence that a property falls into each of the 4 flood probability bands shown here. So that's the basic brief, which we have from Adam, who I think is, thank you very much. And so there's explicit restrictions in that brief, but there's also an interesting implicit restriction, which became more and more interesting as we thought about it. So basically, that's what you'd like to analyze in an ideal world. That's an example of river flow versus time. Effectively, what you're doing with this kind of data is you've binarized it, and so effectively you're working in ones and noughts. And this is, obvious in one sense, is obvious, but it's interesting because effectively what it means is that you're replacing your data with a coin, a fair or unfair coin, let's say. So in other words, you're saying one side of the coin is, a benign, leafy English countryside, and the other side of the coin is a visit from, well, obviously whoever's now exercising that role. But it's hard to tell from that picture who's feeling more grim about the whole business. Actually, I'm sure. Well, actually, the people in the houses, obviously. But anyway, yes. So, in short, what with this remit, what can we do and what can't we do? Well, obviously, we can't make a physically based model which takes into account all possible causes of flood, or a statistical model to estimate the return level from the peak flow, or indeed the mythical black box that needs no twiddling, or a model for ungauged locations, because we need data of some sort. What we can do, and would assert that we have done, is model the probability of flooding at a given location for which we have enough historical occurrence data, and we'll say a bit about what enough would mean, and please ask about that. Create a transparent tool in terms of transparent in its assumptions, and indeed I think we would say that in many ways what we're trying to offer here is a proof of concept straw man. By all means, tear it apart, think about it, but it formalizes the problem in what we hope is a useful way. And via the way we formalized it, it should be able to give you some estimate of how likely it is that any given area sits in a given risk band as specified. So we'll show you what that means in practice, but that's what we've tried to do. So we really have basically gone to a binomial model which is based on the core Bernoulli idea of saying the probability of a flood, the probability of heads, let's say, is theta, probability of tail is 1 minus theta. Look at n Bernoulli trials, which is this binomial model, so look over n years. The probability of x floods being seen in n years is that guy there. So theta to the power of x for what the times it's flooded, and 1 minus theta to the n minus x when it hasn't. And that is the model. But the model has to be, we actually know more than that. The model is the experiment, if you like. So we want to actually feed in something else. We want to feed in the fact that we don't come completely naive to this experiment. So we want to express our prior knowledge. So in other words, the community, the local authority, ourselves, the EA, all sorts of people have some estimate of what the risk of a given, at least one flood occurring in a given year is. In a Bayesian framework, you can explicitly use that as well. So you do two things. You bring in prior knowledge, and you do an experiment on the given piece of time series data that is in front of you, and you merge these things together and you get an output estimate. That is the joy of, the joy of Bayes, if you will, a book that I don't believe has been written, but anyway, who knows? Anyway, I'm too old. I'm of a generation where I'm afraid that kind of summons up all sorts of, anyway. Theta divide, so what we want to do is essentially put what's called a prior, a probability on this rate of flood, and that's what a prior is. It's a probability distribution, and because this rate is already defined on 0, 1, the beta distribution is actually quite a useful prior. It has various desirable properties that you'll see in a sec, but basically it's also relatively flexible in the sense that you can make it non-informative and basically say, I am not going to take a position at all on whether the rate is 0, 1/2, which would be the unbiased coin, 1, etc., etc. I can, if I want to, make that flat. I can make it this shape, or I can actually do what would, on the face of it, be a fairly sensible prior for the flood situation, where you don't think you are very, very likely to be flooded. You are more, one end is much more likely than the other. Now, if you do that, you can put your prior in and the likelihood of the data you have observed on the assumption of a given distribution into Bayes' theorem, of which this is just the business end, if you like, the bit that really is important. And you can convert your prior distribution, which inconveniently on the spreadsheet is blue, and your posterior distribution, you can convert it into the posterior distribution, which is the red here. And this is what the mechanism does. The mechanism is often quite involved because often you don't have convenient analytic properties, but here you do. You have the prior, you have the likelihood of both tractable distributions, and so you get an exact posterior distribution. And what that distribution, the job that distribution does, just to remind you, because it's slightly non-intuitive if you're not used to this, is that it estimates the distribution of the rate of flooding given a given data set. It's that way round. The rate of flooding is the variable, and the data is the thing you have. So it's non-intuitive if you spent years learning about frequentist statistics. It's actually not so non-intuitive if you're a physicist or someone who actually didn't know that much about it anyway, like me. And it does have the advantage. It's couching you're getting a distribution of the quantity that you're interested in a form that can then be assigned to the bands, with confidence estimates, which are called something different in the Bayesian world, on where in your 4 risk bands it will lie. I've garbled that slightly, but you'll see the example. So in other words, you can, as I say, you can crank the handle. In this particular case, you can get a distribution for this flooding rate conditioned on the data. You can get a prediction for what the mean of that will be. You can get a prediction for what the variance will be, and so forth. And you can see immediately, in fact, that there is a dependence on the length of the data series. So what's actually happening is, as you start supplying measurements and as you start measuring for a longer and longer period, eventually whatever you've chosen for alpha and beta in your prior ceases to affect strongly the mean. But there is no magic in this. The point is, it will be affected by your prior, but it formalizes the fact that no experiment revolutionizes your knowledge unless you do it for a very long time. To a physicist, I personally like that. Not everybody does, of course, but that's my bias view. So we've done this, I say we, I didn't actually write the Excel, but it has been done in Excel. Here is the example that actually shows, I think, the brief here. In other words, it's 7 events, X is 7, in 115 years. We had essentially to take a guess as to how long the time series is, and we ended up deciding it was 115. That's important. We'll come back to that. But it returned, and this is on in the relatively informative prior estimate of alpha is 1, beta is 4. So the prior looks like that. it gives you a distribution of what it thinks the flood rate is, if you like, which is this red curve here, and it gives you how likely it is, that flood rate is to lie in band 4, in this case 95%, band 3, band 2, band 1. Okay, so that's what it does. Okay, and the first caveat is, as I say, there is no magic. If you happen to be just looking for 10 years and you haven't seen a flood, but you've also chosen this flat prior, which you might think naively would be the most conservative choice, the most sensible choice, you've actually in some sense fooled yourself, because you've basically said it's, any flood rate is a priori as likely as any other. So the high flooding rates are actually rather likely. And so you get into this situation where you're expected, until you actually get an X, until you actually get a flood, you see 1 over 2 plus n as your mean flood rate. So it's actually a caution which we ourselves were a bit surprised by, against using what might seem to be the most sensible unbiased prior. In fact, using the knowledge you have that you really aren't as likely to be flooded any given year as not, helps you. One of the other things that we were asked about, I think this was number of floods versus number of records. I think that's the idea. I've relabeled it slightly, but you can see that would be a useful space. One of the attractions of this setup is that we can indeed study how the width of the credibility the credibility interval is, which is roughly a measure of how wide the posterior distribution is, and I need to talk to an expert as to how it's done, but it is a measure of how wide our estimate of the flood rate is. You can study how that depends, which is this, how its width varies with the length of the time series and the number of floods you've seen. Okay, and indeed it's interesting that we found, I think Paul found some literature on guideline for minimum viable length of record in this beta case, and I think this is Journal of Royal Statistical Society D. They were suggesting 22. Well, that would be about there, which indeed is interestingly roughly, where it starts to drop down to 0.2. So, I mean, that's interesting. We wouldn't. So, okay. So that's. Can I just check how long I've got now?
10 minutes.
10 minutes. Fine. Lovely. Okay. Thank you. Okay. Well, further work. Well, basically, Adam gave us a good list to start off with of potential, if you will, complications, things that will make life harder. And one, I think this actually isn't a complication. This is in some sense the ideal data, isn't it? I think so. We'll skip lightly over that. The mythical beast, and we'll talk. I think I've got time to talk a little bit about what we've got to do with these 4 things. But I would encourage you, if you have questions about any of them, please ask them, and I will probably direct you to the experts. But there you go. Skewed record, though. I think the skewed record would be an example. So skewed record is one where you've got everything happening at one end except for 1818. That's the. I think it would be fair to say the skewed record is an example where you essentially would have to adopt a somewhat different method. There are some Bayesian methods, but you could use logistic regression to detect trends in the number of events. You could use a point process model if you have enough data of the right type. You could look at the actual flood poor and flood rich periods, and we talked a little bit about Markov models where you actually look at how something like a random telegraph where the levels flip up and down to look at clustering. You could explore the idea of giving higher weights to more recent records, but I think it would be fair to say, and I'm looking at my colleagues there who may well disagree, but I think all of these demand more data than are in that record. I think that's a fair state, or more qualitatively different types of data, but I'm happy to be, for them to chip in now or later if that's not quite right. False negatives, I think, which would be where, say, 1818 was missing, I think we would say they really are a problem, because in the formalism that we're working in, it is crucial to know what n is. I mean, you can do sensitivity to various possible starts, but you can't sort of dispense with having an idea of how long your time series is. I'm told that it is possible to estimate it if it's unknown on the assumption of stationarity, but we're already in a world where we don't really trust that, and in fact we think that might be a more that might be a more serious problem than not knowing the length of the time series. I don't know. That's one. These are really flags in some sense for multi-peaked events. I think there's a, if you like, so you know it would be here. Multi-peaked events, you have a basic tension that. You know, there are statistical ways to look at number of flooding events per year rather than the binary did it flood this year or not, with, for example, a Poisson distribution, and still in this Bayesian framework, because there is, for example, there's an analytic conjugate prior for the Poisson distribution, which is the negative binomial. So you can actually do it analytically. You could, in principle, do it in the spreadsheet again. The problem is that there's, in some sense, a tension between the hydrological perspective and the statistical perspective, because statistical methods tend to prefer independent events. The hydrological perspective will be tending to say, yes, but we know that these are naturally paired events. So there's a kind of dialectic, to use a good word. Anyway, and then finally, here's one we actually were able to do something with as a sort of demonstrative level, is basically say, well, if you've got really short records, like you've just been watching for over 4 years and it flooded 3 times, well, you could put in, I mean, in this case, we're watching 3 years and it flooded twice. You can put it in, and encouragingly, it decides you're in a very high, you're in band 4. But it gives you a rather wide prior. That's the problem. It hasn't had time. Sorry, not prior. It'll give you rather wide estimate of the posterior. So in other words, your estimate, the confidence limit of your estimate of this rate is somewhere between about 0.1 and 0.7. So it's between about there and there. Okay, so it just hasn't had time. It's noticed a lot of flooding, but it hasn't had time to narrow the rate down yet. And so, but. It comes down to the usual statistical problem that, easy to actually evidence if you've got very small n, very small x. I mean, we can show you the credibility interval, but, we have a problem. One of the things that we were asked about, of course, and that wasn't actually on any of those lists, but it was asked about, is climate change. Well, as I understand it, currently flood risk estimates are corrected by a multiplicative factor. So you basically take the quantile at 2010, the 100-year return level quantile at 2010, multiply it by 1.2, and that will be the one in 2050. Or you change the return period. I don't know if this, or you change the return period so that the probability of a flow this year exceeding that level is replaced by a bigger factor times that probability. And you can do an analogous thing in the binomial case. You can replace this theta that you're using or have inferred with a kind of multiplied theta, or do it the quantile way. But more to go beyond that, we would. Well, there are things we can do. There are things we can talk about. But we've given you, we would suggest, we've basically said, as specified, the problem is amenable to a Bayesian binomial model. We have implemented it as an Excel spreadsheet, which I've got on here, if anybody wants to see it, but we showed it in our demo bit earlier. It was interesting to do this, not least because it revealed some non-intuitive aspects of flat priors, which I think for us was actually the single most interesting thing, because whatever intuition I might have had about flat priors was not at all well suited to highly data where one side means something very different from the other. Though I have been in this experience in other fields of science, for example, where you have an instrument that's counting sparse counts and would like to treat them as if ones are as common as zeros, and yet ones are much less common than zeros. So all sorts of intuition starts to go sideways at that time. And I would suggest that we have briefly sketched some approaches to the complications, in quotes, including short series, climate change, etc., and that we feel this model could serve as a useful straw man for the EA if coupled with the spreadsheet and so forth. Thank you.
Does the EA care to comment?
Yeah, please.
Very good. Yeah. Oh, the batteries give out. Yeah, no, they're not. There you go.
Well, I think I can hear you from here. Yeah.
Okay.
Yeah. You hear me? They may not be able to.
It's live stream.
Do you understand?
It was red, right? No, I did turn. You
I'll
just
speak
have to
loudly.
speak loudly, yes.
Thanks very much. It's really exciting. I like this idea. I was a bit when I first sat down with you and you guys said this is A-level maths.
I don't.
We had
Well, I didn't say that because it wasn't in my A-level gov, but I disclaim that belief. But anyway, carry on.
But in any case, I'm
Yeah.
glad you found something
Yeah.
interesting about the challenge, which is great. This output sounds like just the sort of thing we were hoping and expecting for,
Okay.
which is exciting. A couple of questions. The
Yeah.
prior knowledge,
Yeah.
the some bits of prior knowledge that I know computers have access to is they'll have those broad scale national maps.
Yeah.
I gave my example. So you could say that we know that properties are going to be within either band 3 or 4, isn't it, within your very significant or significant.
Yes. Yes.
So you might be able to train that.
We could tune the prior based on that, for example, relatively easily, because it's already. I don't know where the mean of our toy prior. I'm looking at Ilaria just in case you can remember where the mean of our 1-4 prior lay, but it was about 1 in 12.
It was actually still quite towards the flooding.
Yeah. So.
I'm not sure.
I think that will be the point of contention between the EA and the local community.
Yeah, it is the prior is where the proverbial rubber meets the proverbial road. That's exactly where, and we would think. To me, the virtue of the Bayesian approach is it makes it clear that conversation is real, as we all know. But it's the place where it happens before you take in new data to, refine it. In that sense, it is just, to me, as I say, the beauty of Bayesian stats is it's the scientific method formalised. It's a really nice thing in that sense, Obviously, that's not any help to you if you're in the town hall having an argument with somebody, but that's that's how it is.
So yeah, I think we can use the national maps. I think there's also there is information. Are you aware of the multicolour manual? That's what we use to assess flood damages. But
As I say, I'm the one who knows least about this.
if you knew nothing about
Yeah.
your properties apart from they're in the
Yeah.
1 in 200
Yeah.
floodplain, there's a distribution you can use for where properties are spaced and which bands. And in finer grain than you've got here.
Okay.
So we could use that.
Yeah.
I suspect it's also different for different sources of flooding. So we might want to have a drop down which sort of says fluvial or surface water.
One could do that. Yeah. I think one of the many messages that we would convey is that there's the whole Bayesian boom, for want of a better word, is in part powered by the fact that computational Bayesian inference is now easy to do, relatively speaking. It's only that once upon a time having analytic forms was really handy, and they're still useful for demonstrating the core idea, but there's nothing that would prevent you working with an odd-shaped prior now at all, or indeed a more interesting likelihood distribution. I think this just had the virtue of being in some sense. I mean, one of the questions I can't answer, but I think is interesting, is this in some sense the most reassuring estimate? In other words, do all the complications put you in a more likely to be flooded state or not? And that's almost, I'm looking at a real mathematician there, but that's almost a well-posed problem. I don't know, but it's a refinable problem that you might be, somebody might find useful, because even knowing that might be actually quite a useful thing to know, I would have thought.
Are there more questions from the... Yes,
Yeah.
can you speak? I don't know if this one works. Is it?
I'm trying to shout if you want to.
It's better to use the microphones for recording.
Oh, okay, yeah, for sure.
Live
No worries.
stream.
Is it-
Vincenzo checked it is working.
Is it working?
Yeah.
The light doesn't show that. Hello? No, Hello? Yeah.
Yeah.
Good.
Hold it under your name.
Thanks so much. Hey. Hey.
Hello.
Awesome. So one of the saving graces could be that some priors affect the posterior a lot more than others, and I
Yes.
think as you're working in the tail end distribution here, I think your results could be like helped by a sensitivity analysis on the prior.
I'm sure
So
they could be.
it works in like a grid format where you have lots of different priors and you just see how sensitive your posterior is to the difference in them.
I am sure that's true.
Cool.
I'm sure that's an exciting MSc or something for somebody somewhere, or a,
Exactly.
a contract, or who
Very
knows
yes,
what. but-
question, can you pass the mic?
Just a couple of things.
Yeah.
One is if you had to condition your prior using the flood map, which has things up to flooding up to 1 in 1,000 years. How would you set your n?
N is not a property of the prior. N is a property of the data. It would,
Okay.
the N and X come from your experiment. Okay. So basically, this is what you do. You do an experiment that produces data of length n and gives you an estimate of the flood rate little x. The alpha and beta parameters go into the prior, and they don't know about length. They know about anything else you know, but they don't explicitly know anything about length of prior data. Implicitly, though, if you've got very good past data, that will give you a much more, a much better chosen prior. Absolutely, but it doesn't appear. Little n doesn't appear explicitly. Little n does not appear explicitly in these prior distributions because as I say, the Bayesian format really is separating what you know from whatever else you've done before from the n points in the experiment you have just done.
Yeah.
Okay.
Thanks. The other brief one was, did you look at the change in probability for changing between bands, which is important? And if you could do that with this, could you then look at the difference in the flow if you had a flow record and then translate it?
I might actually look at the combined statistician and hydrologist in our group for that. The answer to that. Say that again slowly. Sorry.
So it's interesting to know about, the probability. You might want to shift a property out of one probability band into another. So can you look at the difference in probabilities and then translate that to a flow? So that would give you a sort of standard of protection to work towards.
Well, the flow would be based on the national map again, right? So, yeah, I mean, well, once you move the thing into you will know what is the flow that you have estimated for the 130 year.
I mean, the only thing about this thing at the moment is all it does is give you your current banding in some sense.
Yeah.
It doesn't to use it to decide what band you. It gives you a recent data-based estimate of what your current banding ought to be. Now, if that has indeed moved from where you thought you were, maybe indeed that could be back translated into flow. But I more than that, I don't know.
Last question, quick answer.
Thank you.
Yeah.
There is one issue which you have, so to speak, stepped right over.
Fair enough. Yes.
When you set up the binomial model,
Yes.
or it could be a Poisson model or whatever,
Yep.
you have made the assumption that the occurrence of a flood event now is independent of the occurrence or non-occurrence of a flood event at some other time.
Absolutely, which is probably very dodgy. Yes.
I was going to raise that
Yeah,
point,
yeah.
and in particular in
Yeah.
areas which are protected by flood defences, the occurrence of a flood can damage the defences
Yes.
and make it therefore more probable that a flood will occur in future,
Yes.
so that they're not independent. I
Yes.
don't know how important that is in practice, but it's an issue.
Well, it could be very important. My only thought is that we in some sense lumped it here. You could imagine a state-dependent model, I think, relatively easily. I mean, to me, the closest analogy is, for example, there was a debate in the early 60s in communications about whether, errors between, errors in communications lines knew about what the last error had been. So it's that kind of modelling. So you could do something a bit like that. How quickly the convenience of the Bayesian process goes if you do that. I would have thought that might actually be quite tractable if it was just state dependent.
I think the Bayesian process could stay.
Yeah.
It's a case of what is the probability model.
Absolutely, and I think
critical.
I think nobody but a real optimist, and I'm just not that much of an optimist, would claim that this is that's plausible, but it is in some sense the baseline. It is the baseline if you've got one or data, and indeed I suspect state dependence though might be one of the few things you could in principle do with binary data if you wanted to.
Yeah. Then let's stay at the baseline for now because
Yeah.
we should continue. Thank
Okay.
you.
Oh, sorry.